Hello. This is a video about Pythagoras' theorem, and in particular two proofs of that theorem. I'm Paul. This is me, but you don't need to worry about that. Let's get on with looking at the theorem. Let's first of all remind ourselves of what the theorem says. So this is the theorem, essentially, and it says that it's for a right-angled triangle. It works for any right-angled triangle, but it works only for right-angled triangles. And it says that the square on the hypotenuse is, in area, this is a theorem about areas of squares, in area, it is equal to the sum of the areas of the squares on the other two sides. So again, as I say, this is about areas, and if we look at it pictorially, we have this. I've drawn, not very well I admit, a right-angled triangle, with that being the right angle there. And I've drawn the squares on the two sides of the triangle that are not the hypotenuse, those two squares there, and I've drawn the square on the hypotenuse. And the theorem says that this square in area plus the area of this square is equal to the area of this square. And as I say, it works for right-angled triangles and only for right-angled triangles. Now, the theorem has a number of uses, and historically, it might have been used for constructing right angles, for example, on land to build buildings, walls at right angles, or for building something in a field that needed to be at right angles. And so, for example, if you take something like a string and post or rope and post, and you have three poles, and you have the poles at the vertices of the triangle, and you have the ropes of 3 meters, or 3 meters, 4 meters, and 5 meters, and then you just stretch them out on the ground so there's no slack, you will end up with a 3, 4, 5 triangle, which will be a right-angled triangle. And you know that because 3 squared plus 4 squared equals 5 squared. 3 squared is 9, 4 squared is 16, and if you add them up, you get 5 squared, that is 25. So historically, that was one of the things that Pythagoras' theorem might have been used for. It does have modern applications as well, though, because it is also used, and indeed directly used, for the time dilation formula for Einstein's special relativity theorem. And if you want to learn about that, there's a Wikipedia link there, and perhaps that might be for another video, but it relies directly on Pythagoras' theorem. So it is a theorem with modern uses as well as old uses. Okay then, let's now start to think about the proofs. Now, I'm going to give two proofs of this theorem. The first, I think, is in essence what Pythagoras did himself. It's a very literal proof. It looks at the triangles and it looks at their areas, and it proves quite literally that the areas of the two sides add up to the area on the longer hypotenuse line. And then secondly, we'll have a look at a more modern, or I would say more modern, and I reckon simpler proof. But I think this uses techniques that probably weren't available in Pythagoras' time 2.5 millennia ago. Okay, then let's make a start. We start then by drawing the right-angled triangle. This is exactly the same one actually as I had drawn before. And we put on it the squares on the two sides. There we are. And as I say, I haven't drawn it very well, but you need to imagine that these are all right angles because these are squares, and therefore that this is a straight line. This only works with a right-angled triangle, and it's important for the proof that this is a straight line. We then draw on the square on the hypotenuse, which is there. And as I say, the plan is to prove that the sum of this square and the sum of the area of this square add up to the area of this square. We now draw another line. This time we start at the right angle and we drop a perpendicular onto the hypotenuse and continue through to the other side of this square. Now, the way the proof works really is to prove that this area is equal to that rectangle area, and this square area is equal to that rectangle area, and that's how you show that the two areas add up to the square on the hypotenuse. So we're now going to draw two more lines which form two triangles. So we do this. We draw a line from the right angle down to this particular vertex on the square of the hypotenuse, and we draw a line from this angle, from this vertex of the triangle here, across to the opposite square, the only corner that will draw a triangle. So we're looking at these two triangles, and we're going to show that they're the same area, and that the proof will continue from there. Okay. Now, the next thing we're going to do is just to show that these are right angles, because these are squares, but we need to know that. And then we're going to label the sides lengths. So the length of the shorter side is A, the length of the longer side is B, and the length of the longest hypotenuse side is H. I've drawn these unequal, but it doesn't matter if they are equal, as long as this is a right angle, the theorem, the proof will work. Okay, now because these are squares, we can also make sure that A, that B, that H, and so on. And the other thing we'll do is we'll split the hypotenuse into the lengths X there up to that line and Y beyond the line. So that's what we've done so far. Now, we've only done, this only is for half the proof. We do the other side later, but they're identical. So we'll just concentrate on this side for now. Now, we've got two triangles, and I've got now colored them red and blue. And what I'm going to show you is that these triangles are congruent. They're actually identical triangles. And actually, the red one is simply the blue one rotated 90 degrees to the left. Because they're congruent, they have the same areas. And we're going to show that the area, that one of them is half the area of this square, the other one is half the area of this rectangle. Okay, let's continue then with the proof to show this. So we have the angle between the internal angle of the triangle here, which is L, and that's going to be important in our proof that they're congruent triangles. So let's look at the area of these triangles. Okay, now first of all, we need to show that they're congruent. First of all, they both have a side whose length is H, the two sides of this square. They also both have a side whose length is A, the two sides of this square. And if you look at their internal angles here, they're both equal to the right angle plus L, that one. And for the red triangle, that one. So you've got two sides that are the same, and the angle between them is also the same. And that is a perfectly good test for congruency. So these triangles are definitely congruent triangles. They are identical. It follows that the areas of these triangles will be the same. Well, let's start with the red triangle. What's the area of the red triangle? Well, remember the formula for the area of a triangle is half the base times its perpendicular height. Let's take the base as being A, okay? Now, what's the perpendicular height? Well, that's the perpendicular, so the perpendicular height is also A. Now, it's not actually all that easy to see here because this triangle is so skewed to the perpendicular. But if we draw out this line here as a straight line, continued as a straight line to here, and draw that in, so we've now made essentially a large rectangle. Obviously, that side is going to be A because it's a rectangle. And now you can see quite easily, I think, that that is the perpendicular height. So the area of this triangle is A squared, A times A, over 2, base times half the perpendicular height. Now let's now have a look at the area of the other triangle. So that's, okay, let's have a look at the other area, the other triangle. And now what we see is that the base can be H. If the base is H, the perpendicular height, this time it is fairly obvious, is X. And so the area of this triangle is HX over 2, half the base times the perpendicular height. So the area of this triangle is A squared over 2. The area of this triangle is HX over 2, and they're identical triangles, remember. And so we can see that A squared over 2 equals HX over 2, or A squared equals HX, or if you like, the square of this square in area is equal to this rectangle in area. So that now completes the proof for that side. Now we go on to the other side. All we have to do now is continue exactly the same way for the other side of the triangle. And now what we do is we construct again blue and red triangles exactly the same as before, but using different points. And again, we're going to show that they are the same, they're congruent. In fact, the red one is simply the blue one, this time rotated 90 degrees to the right, clockwise rather than anti-clockwise. They both share these sides H, they both share these sides B, and the angle between them is a right angle plus this internal angle here. And from that, again, looking at the areas, we can say, well, the area of this one is fairly clear, half the base times the perpendicular height, which is, B squared over 2. And the area of this one is base times perpendicular height over 2, hy over 2. So b squared over 2 equals hy over 2. B squared equals hy. So the square, this square here, b squared area, is equal to that area of that rectangle, hy. Now we already know that a squared equals ax. Now we know that b squared equals ay. So a squared plus b squared equals hx plus hy, the sum of those rectangles, which is the same as h times x plus y. And that, of course, is h squared. So we have actually proved that that area plus that area equals that area, which is Pythagoras' theorem. Now, the next proof is slightly easier, I think. This proof for Pythagoras is a very literal proof, isn't it? It actually takes the areas and it shows you how they are equal, quite literally, graphically, how to do it, using congruent triangles, which was a technique known quite well in Pythagoras' time. Now, another proof, this is one that I actually worked out when I was at school, but I don't claim anything for it because I've seen it since many, many times on the internet, and it's not terribly difficult. This uses similar triangles. Now, what we do here is we have a right angle triangle exactly as before, and we drop the perpendicular down from the right angle down to the hypotenuse. And what we've actually done is we've created three similar triangles, and I've labelled the sides D and E, which are these two parts of the hypotenuse H, and then the other sides, again, I'm going to call the shorter side A and the longer side B, and this side here, which is the perpendicular that's been dropped, we'll call C. Now, it's relatively easy to show that these are similar triangles. They share the right angle. There's the right angle for the big one and the right angle for the two smaller ones. They share an internal angle, which must be the same on both. So this angle is going to be the same in both the large triangle and in this particular triangle. And if that's the case, then this angle must also be the same as this angle, simply because the sum total of the internal angles of any triangle add up to 180 degrees. So if two of them are the same, the third one clearly must be the same. And if we do that with the other triangle, again, they share a right angle. Again, it's fairly clear that this angle is the same as, that this angle is shared in both triangles. Both triangles have this angle in, and therefore, because they must add up to 180 degrees, the internal angles, this angle must equal this angle. And so we have three triangles here which have all the same internal angles. It follows from that they're similar. Not congruent, similar. They're the same shape, they're different sizes. But it also follows from that, because they're similar, that the ratios of the sides are the same in each of the triangles. So let's first of all start with the smaller triangle. And we'll just take the shorter length, D, over the hypotenuse A. So we'll call that D over A. Now that's going to be the same as it is for the large triangle. And it's doing the same for the large triangle. The shorter side is A, the hypotenuse is H, so D over A is going to equal A over H. And if we multiply both sides of that equation by A, we get D equals A squared over H. So it's just a multiplication of that equation by A. Looking at the larger of the two of these triangles, and we'll do essentially the same thing, but this time we'll look at the longer side against hypotenuse. So we're going to look at E over B, and that's going to be the same as this time the longer side over the hypotenuse, B over H. Because those ratios are the same, because these triangles, that triangle is similar to the large triangle. So E over B is the same as B over H. E over B equals B over H. This time we'll multiply both sides by B, and you get E equals B squared over H. Now all we do is add both equations together. Of course, that's perfectly legitimate. So we add D plus E, and we get A squared plus B squared all over H. But we know that D plus E is actually the same as H. You see that D plus E is the same as H. So H equals A squared plus B squared all over H. And multiplying by H, we get H squared equals A squared plus B squared, which is, of course, Pythagoras' theorem. So there is a second proof, which I think is quite a lot simpler than Pythagoras' own. That's my personal view. But I don't think Pythagoras had these techniques, whereas we fortunately do. Well, there you have it. You've seen two proofs, and I hope that has been of some use to you. And thank you very much for listening to and watching this video.